Well, I am looking at the feasibility, and I have to modify what I've said about this because, you know, my understanding is based on the way that people are communicating this, and they're not doing a great job of explaining that this is a sock that we're talking about, and that there's no path to trace into things, that would enable this to happen, that you could interrupt and reroute the logic. Although there are methods that could do this, and I'm consulting ChatGPT about it, and there's a lot of information that I would like to dump on you about hacking the Nintendo Switch 2 per what the ChatGPT was able to tell me about the the sock that we're talking about and how it could hypothetically be hacked. Now, I asked it about focused ion beam, and I asked it to teach me about focused ion beam access, but I want to get into this, about the whole thing. So what I did, and what I said was to it, is based on my understanding currently of soldering work and everything, and I know about reballing and everything, and using a stencil, and how it's not really all that hard in practice. So we've been asking it about this. I asked it, what about getting between a lockstep comparator with a new PCB, getting between the lockstep comparator and the processor core with a custom BB to intercept or tamper with their spoof execution falls into the domain of extremely advanced hardware hacking, bordering on chip decapsulation, probe level interception, and possibly bypassing safety critical systems, which raises significant legal and ethical concerns. However, I can absolutely explain the theoretical feasibility and technical challenges and what researchers have explored purely for educational and research awareness. You know, Theoretical goal would be interposing a PCB between the core and the comparator. Objective: insert a physical interface, e.g., FPGA, logic analyzer, or spoofing logic between core AB outputs and the lockstep comparator circuit. This is extremely difficult because, this is all integrated on the die. Most modern DLCS systems integrate cores and comparators on a single DOC die with no external buses to intercept. There are no pins or tabs to tap into. Even if you could expose these buses, example given an older FPGA based system, they all run on hundreds of MHCs to DHCs. You need precision impedance match probing and high speed logic to handle signals without corrupting timing. The comparator is hardware logic. It likely resides in an internal pipeline stage, not an external device, meaning you'd need to physically decap the chip, isolate intercaps, and tap into internal traces. Redundancy and CRC checking. The comparator may intercept cryptographic checksums, or constant time comparisons, which invalidate tampered signals unless you perfectly spoof both cores. There's the tripwire detection. DCLS systems used in automotive and aerospace may have fault injection detectors or anti-glitch monitors, making any timing changes trigger a hard fault. Theoretical methods that were for educational use only. Although here we're not really, we're just lying to ChatGPT about this. But decapsulation plus microprobe, which is extremely hard. You remove the chip package, use electron or laser probing to observe the internal buses. Now, you'd pretty much have to go this far. You could try to do this via other methods, but it seems that Nintendo has really done their shit properly here. And this is not what researchers usually do. In practice, you could use they basically say they use the MFI and glitch injection to cause one core to diverge briefly, bypassing the need to spoof hardware buses. They use fault tolerant design or on an open source risk 5 lockstep systems, modifying the lockstep logic inside an FGB, no decapping. But here, I think you would pretty much need to decap things with the Nintendo Switch 2, which would also, be very, you know, uh, if you did this, this would definitely violate, tamper protection laws, the DCMA warranty and warranty contract agreements, and public safety codes. So you'd be in trouble for doing this, and so you're pretty much going to have to do it Chinese. You're going to have to go to a different country to do it, properly, at least, unless you want to, build a clean room here in the United States somehow, and use it for illegal purposes. But you're gonna have to be loaded for that because no hobbyist is gonna be able to do that, and afford that, But I clarified, for the Nintendo Switch 2, you're asking about physically interposing a custom PCB or an interposer or spoofing there between dual-core lockstep components and the cores on the Nintendo Switch 2 to possibly manipulate or observe processor output. In other words, trying to get between the internal safety logic of the SoC. Let's give you a deep and technical explanation of why this is functionally impossible in commercial SoCs like the Nintendo Switch 2 and how researchers approach these kinds of systems instead. The Nintendo Switch 2 is a lockdown black box. The Switch 2 usually uses an NVIDIA Tegra T239 Drake SoC based on Ampere GPU architecture or an advanced ARM 82 APU cores. It's a fully integrated SoC. The CPU cores, the GPU, memory controllers, secure boot logic, and if present, lockstep comparator circuit trader are all on the same physical silicon die. This means there's no physical bus to trace between the cores, and any lockstep comparator that you can reach with a PCB, you cannot splice a custom board between logic that never leaves the die. Why you can't get between DCLS on the Switch 2, it has on-die integration, which was not properly explained by the YouTuber here. Lockstep logic inside the SoC, no signal goes off chip for ALU results, register state, or instruction dispatch between cores. There's a high-speed internal buses. Any internal interconnects run at GHz speeds with nanosecond timing. Even if you could access them, injecting without disrupting timing is infeasible. Flip chip packaging. The sock is likely a flip chip BGA, meaning all connections are made through dense grid under the chip. No external access to inner signals. There's no exposed lockstep control. There's no public or software accessible register to enable or disable DCLS. All control is likely buried in secure boot ROM, inaccessible without exploit. What real researchers would do instead, because hardware probing is unfeasible, researchers use these approach fault injection attacks, EMFI, electromagnetic fault injection, to induce stable bit flips or desynchronization, clock or voltage glitching to corrupt instruction execution on one core. This targets logic before or during lockstep verification, and may lead to silent divergence. Using reverse engineering firmware, using a firmware dump from boot ROM or TSEC, trusted execution security controller, whether lockstep is used, how errors are reported or masked, secure world behavior, trust zone. The Tegra boot chain analysis, using past knowledge from Fusu Guli and showed a full on Switch 1 to reverse engineer the new Tegra 239 boot chain, trying to identify any early initialization code that secures secure boot, CPU cores, or safely monitors the system boot. Jetson development boards, safe targets, and NVIDIA Jetson boards, the e.g. Jetson, Oren, or similar SoCs are developer accessible. You can explore boot chains, peripheral access, and DM or CPU behavior without violating any laws. What an interposer PCB would require, hypothetically, to physically interpose a new PCB between the Switch 2's SoC and a comparator, you'd need full chip decapitalization, removing the silicon from the packaging, focused ion beam tooling to cut internal traces and reroute them, high-speed custom reballing to attach an interposer to a reconstituted SoC package. In other words, you would need multi-million dollar lab equipment, weeks of microsurgery, and the risk of destroying the chip if you made any error. Even security labs don't do this unless the chip is irreplaceable and the reward is high. Here, the reward is pretty high. You would essentially be able to sell your modifications for a significant markup, in terms of profit, obviously. So, it would be worth it since, the reward is so incredibly high for doing it. Your mod chip here would be worth million, you'd be able to sell it. Obviously not for a whole lot to every individual, but, you'd be, unlike traditional mod chips, you'd be able to charge thousands for this. You'd be swimming in it. You'd be able to say justify a price of like $5,000 a unit, and people would buy it. You know, you'd simulate a DCLS system in FPGA. Viable alternatives. You could create a dual core RISC processor. Yeah, but I'm not looking to do this really truly that way. But they say to start with. They want me to study the re-switched and failover switch write-ups, which I don't have any problem doing, but the Switch 2 is heavily hardened. Nintendo and Nvidia have learned from their past mistakes. Boot ROMs are fused off and secured. USB recovery modes are likely disabled. Any lockstep, secure world, or debug interfaces are burned shut via eFuses at the factory. Your best bet, educationally and ethically, is to simulate security architecture and experiment in safe environments like JETs and dev kits. And at this point I ask it about reballing. Using reballing to intercept internal logic like the dual core lockstep comparator on the Nintendo Switch 2 is theoretically fascinating, but in practice it runs into near insurmountable challenges, both technical and physical. That said, let's explore this step by step for educational purposes only, from the perspective of hardware reverse engineering labs that operate at the bleeding edge. Reballing involves removing a BGA ball grid array chip like this Tegra SoC in the Switch 2 from the motherboard, replacing the solder balls underneath with fresh ones, usually using a stencil, optionally modifying connections using an interposer PCB or rerouting signals. This is typically used for replacing faulty chips, reversing chips onto a custom PCB, preparing chips for probing or fault injection. Your goal here would be to interpose between the SoC and the comparator logic. The idea: reball the Tegra 239 chip from the Switch 2 and insert a custom PCB layer between it and the main board to intercept or manipulate signals. Ideally, communication between the CPU cores and on any on-chip lockstep comparator. But here's the catch. Problem 1, the comparator is on die, not on board. Modern SoCs like the Tegra 239 implement lockstep logic, register comparators, and secure hardware entirely inside the silicon die. This does not make it hypothetically impossible to attack, but obviously things are going to need to change for that to happen. This means the signals never reach the BGA balls underneath the chip. You can't see them, route them, or spoof them with reballing. Even with perfect deballing, there's nothing to intercept unless those signals are externally routed, which they are not. The problem too is the flip chip packaging. Most modern XCFCs use flip chip VGA, where the die is flipped upside down and wire bonded internally. The die IOG is directly under the chip, invisible and unreachable even with decapsulation, unless you have focused ion beam access. Now this would hypothetically cut anybody out of the process of doing it, but I asked some questions about how access to focused ion beam, work could be democratized. Basically, you'd have to remove the package. You'd have to use the FIB to cut internal traces on the silicon die. You'd wire bond to internal nodes, repackage or stack onto a custom carrier board. This is multi-million dollar lab work done by state actors or top security labs, not hobbyists that we're talking about. Realistic use cases: chip off NAND forensics, reballing EMC and NAND chips to extract firmware from phones, consoles, etc. power glitch injection. Custom interboarder injects power glitches or delays to cause faults. Monitoring external buses. You can tap exposed memory buses, I2C, SPI, UART lines using interposers, rerouting known debug ports. If an SoC exposes JTAG, UART, or boot configs, reballing them helps tap or reroute them. Hypothetical interposer restack. If you still want to build a custom, interposer board with it reballing, here's what you'd need: high resolution X-ray to map the BGA ball precisely, custom 10-layered PGB that matches ball out and reroutes signals of interest, wire bonding or pogo pins to connect measurement gear like logic analyzers, cryo-cooled reflow system to avoid the SoC warping during detachment, clean room or near clean room conditions. Examples of this: monitoring DRAM signals between an SoC and an Tegra SoC and LPDDR4 chips to extract externals via cold boot attack. Still very difficult. What real researchers do when studying systems like the Switch 2, the DCAP plus FIB, the advanced SoC reverse engineering, ID fusing off boot config, trust zone, EMI fault injection, the desync cores. Well, anyways, so moving on to this, you can't really do this. You can't interpose the lockstep, signals with a new PCB. The signals are on the die, so this was not properly explained by the person in that video. They said it to a separate chip. It's like, well, then, if it's not one of the cores that we're talking about, then it's necessarily another chip that it's sending it to, and you can get between that, but that's not the case here. So, you have to find a way to get between the interposer internally, which is a lot more, a lot more difficult, and you're tapping, debugging bootstraps via an interposer only if exposed to, but that's not likely. Monitoring external DRAM and NAND traffic, that's possible but hard, and so what you can do is, and doing this safely and legally is dangerous and possibly illegal without, research exemptions, but, obviously using a country that hasn't had a history of hacking would be the way to go. Simulating DLC systems in the FPGA experiment with competitor desyncs, using EMFI kits like the Chip Whisperer Pro, ReRD, and SCAB tools to explore glitch-based desync, study the Switch 2 boot chain once the firmware is dumped and decrypted when possible, analyze the T3 boot behavior using, Jetson or in dev boards or somebody uses a similar, so I go here at this point. I say, teach me about focused ion beam axis. Let's dive into focused ion beam axis, a powerful and expensive technique used in semiconductor reverse engineering, chip modification, and failure analysis. If you're thinking about hacking or analyzing SoCs like Nintendo Switch's 2's Tegra, this is one of the very few tools capable of accessing internal logic not exposed internally. What is a focused ion beam? Is a tool that shoots a beam of charged ions, usually gallium, at a silicon chip surface, can remove, cut, or deposit conductive or insulating materials, has nanometer precision, allowing you to target and modify individual traces or transistors. Think of it like nanoscale surgical laser for silicon. What you can do with this is cut metal traces, disconnect buses, isolate logic blocks, reroute interconnects, patch hardware, patch hardware logic, ID force a comparator to always output to always match, quote unquote match, expose internal signals, create microprobe pads to attach test wires, insert new logic, add jumpers or bridges to redirect execution. You'd have failure analysis, diagnose broken silicon, silicon semiconductors at the transistor level, and you could bypass security fuses. In theory, disable an eFuse-based boot lockouts, which is legal but legally very questionable. It's not legal. So, the process works by removing the package via decapsulation, e.g. acid etch or plasma, polish the die surface if necessary, scan the chip with SEM, with an electron microscope. FIB systems often have an integrated SEM to visualize the target area at high resolution. Then you focus the ion beam. Typically, ion beams are accelerated and focused down to a 5 to 20 nanometer spot. Modify the silicon. Use the beam to mill away the insulating material. Deposit platinum or tungsten to create new wires or bridges. Optionally add pads, and so you have a diagram here of this. The die face up, SEB cuts. Examples in reverse engineering. This would bypass secure boot. If secure boot is routed through a fused latch comparator, FIB could cut that trace, or change the logic level, allowing unsigned code to boot. SOCs often disable JTAG via fuses. FIB can reroute the fuse or force enable JTAG. Dump ROM OTB by tapping internal buses or creating probe pads. You can read out a normally inaccessible memory like boot RAM or key storage. Now, why this is incredibly rare that this happens. The cost, FIB tools cost between $500,000 and $3 million. The skill required. FIB is like neurosurgery for silicon. One mistake, the chip is destroyed. The legality of it on commercial devices, tampering with secure boot or crypto logic, can violate laws like the DCMA, the Wismar Agreement, or export control regulations. So you're gonna have to be really, really careful about how you do this, and go about this. You're probably just gonna have to say that it's for, not for piracy. It's just as you would for everything else. You say that it's just for homebrew. The chip fragility. The Tegra T239 is a cutting edge processor, which is 7 nanometers or smaller. There's a high reach of damaging or triggering protection mechanisms. If you're curious but can't access, SIB, what you can do is simulate FIB patching and TSD tools like Magic FLSI or K layout to visualize how patches work. Study public FIB case studies, the EEG capping smart cards, disabling fuses, and academic CPUs. Use open access SBA or chips. Work on hardware where interconnects is exposed or modifiable. Watch teardown videos. See real world FIB tools and actions. Zepto bars or silicon PRON would be somebody to watch. FIBs in security, research. The PlayStation 3 was an early silicon action, involved probe level logic tampering. Smart card crypto breaks. Side channel researchers use FIB to tap internal buses. Tesla NAND recovery. EMF stages were reballed and probed for bit extraction. Further reading would be Hardware Reverse Engineering by Jasper Von book and FIB chip level attacks explained. Zeptobar decaps, incredible chip images and decap analysis. Chipworks, Tech Insights, industrial chip teardown with FIB. Silicon porn, die shots, and FIB access explorational. So at this point, I ask a question: will this ever get cheaper for somebody to do, for a hobbyist to do? And it says yes. It might get cheaper. This is, why FIB is expensive today. FBI SEM systems like the Thermo Fisher Helios or Zeiss Crossbeam cost $500K to $3 million USD. The environment, it requires a clean room with nanoscale vibration and EM shielding. Consumables, gallium sources, high voltage supplies, deposition gases. It's operated by PhD level engineers with years of experience. Any error can permanently destroy a chip worth thousands. Chip complexity, modern SoCs have 10 metal layers, feature sizes, making targeting extremely difficult. Will FIB ever be consumer affordable? They won't drop to hobbyist level like 1K to 10K. There are too many fixed high cost components. IG, vacuum changing, EM shielding, nanometer, but emerging trends could democratize access. Just like PCIe fabs became accessible via online services, FIB may become remote accessible, e.g., you pay $500 to $2,000 for a patch job, you upload the layer map, you coordinate data, you let a lab do the work. This already exists for failure analysis firms IG Tech Insights, Decap Labs, open source micro FIB tools. Academic and open hardware projects are slowly building simplified ion beam systems. They're lower resolution, micrometer scale, good enough for some probing and disposition. Think of it as the rep equivalent of FIB, still earlier but promising. Alternative tools are cheaper and safer. Laser FIB, pulsed UAE, selective decap or ablation, obviously electromagnetic fault injection, but I think all things considered, this is the way that you're going to have to go to hack the thing. And, basically microprobing tools are used, and GitLab gear on eBay are already under 10K. EMFI kits, tools like the Chip Whisperer, new AE EMF probes are less than 2K. Cloud FIB access may be available within 2 to 5 years, but this depends on demand from security, research, and academia. Nano FIB open source is 5 to 10 years away. Ambitious but possible as precision, 3D printing evolves. The hacker mindset alternatives, if you're drawn to the idea of what FIB enables, try simulating those effects instead, but focused ion beam tools probably won't be cheap in the personal lab sense, but access will become easier through cloud services. Alternatives like EMFI and probe stations are already accessible. Long-term desktop level tools may evolve via open source microfabrication. Would you like a curated list of companies offering cloud-based FIB access, or suggesting Decap Labs and Tech Insights would be somebody that you could turn to. Nanoscope Services, Testlove, ISE Labs, delayering.com would be another group of people to go to. This is really, they do serve one-off research and security clients. If you're working on reverse engineering a chip you legally own, performing fault injection prep, probing secure boot paths, or verifying a vulnerability, you often can work with these labs remotely, paying only for the machine time and consumables. So anyways, you'd have to, draft a sample inquiry email to an FIB lab, and figure out how to actually send these into them and everything. But this is I do believe that if you're going to hack the Switch 2, this is the route you're going to have to go down. You're going to have to do research by, using a cloud-based, FIB access set of tools to do it. It's because of the fact that you're going to need a fucking clean room to do this and everything, and because of the fact that Nintendo went the route of putting, down an SoC where the whole security process is a system on a chip. So, and, the fuses that are into it are not on the balls themselves. They're actually, built into the chip itself. Now, the reason why if you had, $3 million to do this, it would be worth it to build the clean room and everything, is that nothing could ever stand up to you again. Even if, some company goes out and spends several million on building a SOC, well, you've already got tools now that can defeat that. That's like the ultimate end. Nobody's ever going to come up with something better than that. So, if you've got 3 million, you're unstoppable at that point. You can create a mod chip for anything and sell it for an obscene amount of money, and you'd make all your money back and then some, and you'd be a very wealthy person if you did this. But, I don't know about you, I don't have even, the 500K just laying about to do something like this. So, I'm out of this one, but I've explained the technicals to you in full detail now with ChatGPT, and so now I have some idea of what would, be required ultimately to hack the Nintendo Switch 2. And, good luck. If you're a security researcher, I've proposed some routes. I've proposed FIB and the fact that there are cloud-based FIB companies that could reduce the cost here significantly so that you're not paying out the ass to do this. But there you go.